Now, as I mentioned yesterday when we were looking at domain and range and whether or not something is a function, the easiest way of telling is by looking at the picture. So there is quite an advantage of knowing what basic curves looks like. So let's just go over our basic curves and basic ideas behind sketching graphs. The numbers on the axes, of course, should be evenly spaced. You need a good scale. That doesn't mean that the y-axis has to have the same scale as the x-axis. Sometimes that would be impractical. Imagine if you were trying to draw a graph of y equals x squared plus, say plus 1,000. Then it would be very impractical to have the same scale on the x-axis as y. Whereas other shapes, it's absolutely necessary you have the same scale. For instance, if you were doing a circle, if your scale was different on the y and x-axis, it would look like an ellipse rather than a circle. Easy points to find. The y-intercept is always very easy because you just got to substitute 0 in, probably the easiest number to substitute. So the y-intercept occurs when x equals 0, and conversely the x-intercept occurs when y equals 0. So if that equation is easy to solve with the y equals 0, okay, we'll go find it. But if it is difficult, we usually don't worry too much. So we'll find our x-intercepts if they are easy to find. Once you've got your intercepts, then it's pretty easy if you know what the basic shape looks like, because you can get your shape going through those particular points. But never forget the most basic idea when you first started sketching lines and curves. Table of value is fine. You don't necessarily have to draw up a table of value, but just pick a point, sub it in. Oh, that's the y value, and plot a few points, and you get a feel for what the graph is doing. So, okay, our basic ones. And I guess the most basic of all curves is a line, even though we still call it a curve. It's a straight line. There we go. Then that would probably be the most basic of all the straight lines. Y equals x. We know in general that y equals mx plus b, where what we notice, if you're looking at an equation, if for some reason you couldn't recognize it was a straight line, you'll see that y is to the power of 1, and over on the other side of the equation you have x to the power of 1, then that tells you, oh, this is going to be a linear function. The highest power of x is 1. Then we move on to our parabola, and all quadratics can be graphed as parabolas. So that's the way we recognize that one. The highest power is 2, so you'll have y to the power of 1, and then the highest power is 2 in the x's. Or of course you could have it the other way around. You could have the highest power of y is 2, and then x is 1. That just means you've got a parabola on its side, rather than our traditional way of seeing it. X-intercepts are usually easy to find, because of course all we've got to do is solve the quadratic. And your vertex will always be halfway between the x-intercepts, because it's a symmetrical shape. So once you've found your x-intercepts, it's very easy to find where that axis of symmetry is, because it's got to be the middle of the two x-intercepts. So average those out, you know what the x value is for the axis of symmetry, sub it in to get the y value, and you've got the vertex. So here we go, here's an example, x squared minus 4x plus 3. I'll do it by completing the square, because when the square is completed, if you remember your ideas from shifting curves, when it's written this way, I can see what the vertex is straight away. Because when it's grouped with the x, then that'll tell me the x value, and the number by itself tells me the shift up and down. So I know the vertex for this one is 2, -1. We'll talk more about shifting curves. I think I've got that planned for tomorrow. The x-intercepts, I would solve the quadratic, and I end up with 2 plus or minus 1. So 1 or 3. So as I was saying, you can see that the x value of the vertex is in fact the average of 1 and 3. Got to be in the middle. And so a quick little sketch. Okay, we've got some key points. And there we go. Once I know those key points, I've got a vertex, x-intercepts. Actually, I didn't bother labelling the y-intercept, but of course that would be 3. And then we can just draw in our basic shape. All right, we then move on up to the cubic. Now the cubic's an interesting one. That's a pretty dodgy one. The basic cubic has that, well, inflecting shape. Okay, so at 0, 0, it's what we call a horizontal point of inflection, but it's where it twists, if you like. Okay. Now that's true if the cubic can be factorized perfectly, so into a perfect cube. Right? So you'll have ax cubed plus bx squared plus cx plus d. How do we recognize it? Well, this time, y is to the power of 1, and the highest power of x is 3. Right? So if it can be factorized to be a perfect cube, or some multiple of a perfect cube, it'll have that basic shape. Otherwise, it'll have that up and down type shape, where you have two turning points. Right? So other cubics would look like that. They're the ones that can't be factorized into a perfect cube. Higher powers. Okay, so all even powers have a U shape. Only the x squared is called a parabola. They have that sort of U shape. So power of 4, power of 6, and so on and so on. But what happens is, as the power gets higher, you'll find that the base of the curve gets flatter and the sides get steeper. So I've sort of exaggerated that there with my U shape. But as the powers get higher, you'll find it gets, shallower at the base, steeper at the sides. Same thing happens with the odd powers. All of the odd power ones will look like our cubic, but again, as the power goes up, flatter at the base, steeper at the sides. So powers get bigger, flatter at the base, steeper at sides. All right, the next interesting shape, I guess, we look at is the hyperbola. And so they're the ones where we end up having an asymptote or two. And there's our most basic one. 1 on x, or sometimes it's written as x times y equals 1. So how do you recognize it? Well, again, on one side, y is to the power of 1. The other one, x is to the power of 1, but it's in the bottom of the fraction. So one's on the top of the fraction, one's on the bottom of the fraction. Or, I guess the other way of recognizing it is if the two pronumerals are multiplied together. Then you'll get some sort of hyperbola. So any time you see a pronumeral in the bottom of the fraction, you're expecting some sort of hyperbolic function. You're probably going to get some sort of asymptote, depending on what the bottom is. Because, of course, remember, the bottom of the fraction can't equal 0. That will create the asymptote. Circles. There it is. X squared plus y squared is the radius squared. So now, when you recognize it, you go, oh, look, both of the powers are 2. So the highest power of both of them 2. But not just that, the coefficients are also equal. So that's important. Like if you had x squared plus 2y squared, that's not going to be a circle. Coefficients have got to be the same as well. In fact, if you had x squared plus 2y squared, you'd end up with, you get an ellipse. If you had x squared minus 2y squared, you'll end up with you get a hyperbola. But it's sort of on its side. It's like it's been rotated 45 degrees. Exponential. So our exponential curve, there it is, goes asymptotic to the x-axis. And then as we go, it gets steeper and steeper, because that's the power of the exponent or the index. Higher the power, the bigger that number is going to be. This is what it would look like if the base is greater than 1. So you have something to the power of x. So very easy to pick an exponential. You'll notice that you've got a pronumeral in the power or the indice. Hang on, before I go on to the next one. If the base was less than 1, and when I say less than 1, I actually mean between 0 and 1, then it would be reflected in the y-axis. So the curve would go the other way around. You don't worry about 1 to the power of x, because, of course, that's just a straight line, y equals 1. And anything negative is a bit difficult to draw, because if it's an odd power, then it's going to be a negative number. If it's an even power, it's going to be a positive number. If you were finding, say, the cube root, so a power of 1/3 or 2/3 and so on, yes, you can do that with a negative number. But if it was an even one, so square root, you can't find those. So you actually just end up with a whole series of what looks like random points. So it's not really a curve at all. So our bases are always positive with our exponential. Roots. Roots usually come about when we get a relation and we want to turn it into a function. So we usually split it into two functions. And there's the classic one, the semicircle. So the top half of the semicircle is the positive square root of r squared minus x squared. But we can do it with other shapes. There's the top half of our parabola. Turns out to be the positive square root of x. Now, if you're unsure and you just see the equation, well, the easiest way of telling with these root ones is square both sides, and then it'll become more obvious which curve you chopped in half. So, if we were unsure with this one, square both sides, we get y squared is r squared minus x squared. We can rearrange that, and we get the equation of the circle. So, righto, it was the circle we chopped in half. And because it's the positive square root, I must have the top half of the circle. With our parabola, similar thing. Square both sides, I get y squared equals x. Oh, okay, so as a parabola, again, positive square root, I must have had the top half of the parabola. So positive square root's the top half, negative square root's the bottom half. Okay, 2G.